Every astronomer who came before us scanned the same sky you can see tonight, and for centuries they were certain they had found the most powerful things in it. Stars, exploding stars, the blazing cores of galaxies. But they were wrong, and the thing they missed was not hiding because it was faint. It was hiding because it was too far away, and because nothing in their imagination was violent enough to explain it. Picture an object that pours out more than 10 to the 40th power joules of energy every single second. Our Sun, the engine that grew every living thing you have ever touched, takes an entire year to release 10 to the 34th. Second for second, this object is roughly 31 trillion times more powerful than the Sunday. It outshines individual stars without effort. It outshines whole galaxies. The brightest of them outshine 1,000 galaxies at once. And here is the part nobody tells you. The same kind of engine is sitting, right now, at the center of the galaxy you live in. Get comfortable. Hit subscribe if you're new here. Because by the end of this, the quiet at the center of our galaxy is going to feel a great deal less like safety. Now, let's slowly ease into this. Part 1. Monsters in the Dark. There are monsters out there, and for almost the entire history of astronomy, nobody could see them. They were not hiding behind the familiar stars or tucked away inside the calm nearby galaxies. They were further out, and they were stranger, and they were so far beyond anything astronomers expected to find that when the first faint evidence of them arrived, the natural assumption was that the instruments had made a mistake. These objects are completely invisible to the human eye. You could stand under the darkest sky you have ever seen on the clearest night of your life, and you would never catch even a hint of them. And yet they are, by an enormous margin, the most powerful, sustained engines in the known universe. Consider what one of them can do. A single one of these objects can pour out more than 10 to the 40th power joules of energy every second. That number is almost impossible to feel, so let us anchor it to something familiar. Our Sun is not a small object. It converts about 600 million tons of hydrogen into helium every second, and it has been doing that for nearly 5 billion years. Over the course of an entire year, the Sun radiates roughly 10 to the 34th power joules of energy into space. One of these objects releases that much energy, the Sun's entire annual output, in a single second. Think about that for a moment. Everything the Sun does in a year, the light, the heat, the radiation streaming out in every direction, one of these objects matches in the time it takes to say the word now. If you prefer to compare them second for second, the gap is even more staggering. Measured at the same instant, against the Sun's power output, in that same instant, one of these objects is roughly 31 trillion times more powerful. Not 31 times, not 31,000, 31 trillion. There is no human experience that prepares you for a number like that, which is part of why this story is so unsettling. We are about to spend the next couple of hours building, piece by piece, an understanding of an object whose power sits that far outside anything intuition can hold. The brightest of these objects outshine individual stars without effort. They outshine entire galaxies, the great spiral cities of hundreds of billions of suns. And the most extreme among them outshine 1,000 galaxies at once, a single point of light brighter than the combined glow of 1,000 separate islands of stars. There are rare cosmic events that can briefly compete. The most powerful supernovae, the explosive deaths of the largest stars, can for a short while flare brighter than these beacons. But those explosions are temporary, ephemeral things. They blaze, and then they fade within a matter of weeks. These objects are different. When one of them awakens, it stays powered not for weeks, not for years, but for millions of years. In just a small fraction of that lifetime, one of them can release more total energy than the most violent explosion the cosmos has ever produced. And they are hungry. They feed on anything that strays too close, and they are capable of tearing entire stars to pieces in a single fit of rage. As they feed, they produce flashes of radiation and jets of charged particles that shoot outward for millions of light years, piercing straight through galaxies and spreading their influence across whole clusters of galaxies. They are the quasars, and they are the most powerful engines in the known universe. Let us slow down and really sit with a comparison, because the human mind is genuinely bad at numbers this large, and the danger is that 31 trillion just becomes a noise, a word that means roughly the same thing as a million or a billion. It does not. Imagine you decided to count to 31 trillion, one number every second, never stopping, never sleeping. It would take you very nearly a million years. That is the size of the gap between the sun, the object that anchors our entire existence, the engine that grew every plant and warmed every ocean, and a single quasar. The sun, which feels infinite to us, which we cannot even look at without hurting our eyes, is, next to a quasar, a faint and almost negligible thing. There is another way to hold the number, and it may be the most honest one. A quasar releases, in a single second, as much energy as our sun releases in roughly a million years. A million years ago, there were no cities and no writing and no farms. Our species had only just begun to look recognizably like us. Everything the sun has poured into space across that entire span, all the light that fell on all those ancient landscapes, all the warmth of all those hundreds of thousands of years, a quasar matches in one tick of a clock. The whole solar history of our species in a heartbeat. And these are not rare freaks, not one-of-a-kind oddities the universe produced once and never again. We currently know of around 1 million active quasars, and astronomers suspect there are at least 10 million more in the observable universe still waiting to be found. 10 million engines, each one capable of outshining 1,000 galaxies. The universe did not build the most powerful object in existence as an accident. It built millions of them, and it built them as a matter of routine, as simply the thing that young galaxies do. There is one more thing worth saying before we begin the investigation properly, and it is about the title of this video, the most powerful thing in the universe. That phrase invites an obvious question, the kind a careful listener should always ask. Powerful in what sense? Because there are other contenders, and they deserve a fair hearing. A supernova, the explosive death of a massive star, can for a few brief weeks blaze brighter than a quasar. The most extreme supernovae briefly outshine these beacons entirely. But a supernova is a death. It is a single, final, unrepeatable event, and within weeks it fades and is gone. A gamma-ray burst can release, in seconds, an almost unthinkable concentration of energy, but again, it is a flash, here and then gone. A quasar is not a flash. A quasar is sustained. It holds that ferocious output not for weeks, but for millions of years. And so when we say a quasar is the most powerful thing in the universe, we mean it in the sense that matters most for an engine. Not the brightest spark, but the brightest fire that refuses to go out. In a small slice of its lifetime, a quasar releases more total energy than even the most violent explosion the cosmos can produce. That is the object we are going to spend this journey trying to understand, and the first surprise is that nobody set out to find it. Here is the part that should make you sit up. We tend to talk about quasars the way we talk about anything terrifying and far away, as if distance were a kind of safety, and they are far away. The nearest one sits more than 700 million light-years from Earth, and the most distant is roughly 13 billion light-years away, a journey that would take nearly the entire age of the universe to complete, even if space itself were not expanding as you travelled. But distance is not the whole story. Because the engine that powers a quasar is not some exotic object that only exists in the deep cosmic past. The same kind of engine sits at the center of the galaxy you are living in right now. It is quiet at the moment. It is not awake, but it is there, and it has been awake before, and it will be awake again. By the end of this, the night sky is going to feel a little less safe than it does right now, and that is not a threat. It is just the truth. So let us begin where the astronomers began, with a few faint, meaningless smudges of radio noise that nobody could explain. Part 2. The pinpricks nobody could explain. To understand how strange the quasars are, you have to understand how unremarkable the universe seemed to astronomers in the years just before they were found. By the 1950s, science had grown comfortable with the idea that our Milky Way was just one galaxy among many. That was, in its time, a revolutionary thought, and it had been hard-won. But once it settled in, the universe it described felt oddly tidy. The belief was that the cosmos was relatively small, perhaps only a few billion light-years across at most, and the contents of that cosmos seemed almost boring. There were galaxies. There were clusters of galaxies. And between them there were vast expanses of nothing. For a while, astronomers allowed themselves to feel that they were finally getting a handle on things, that the broad shape of the universe was understood, and only the details remained. That comfortable picture did not survive contact with new technology. The middle of the 20th century brought a quiet revolution in how we observed the sky. Optical telescopes, the instruments that gather ordinary visible light, were growing enormous. But just as importantly, astronomers were learning to use the rest of the electromagnetic spectrum, the wavelengths of light that lie outside the narrow band our eyes can detect. And the more of that spectrum they opened up, the clearer it became that the universe was far stranger than the tidy picture had allowed. One of the first of these new windows was radio. In the 1930s, a pioneering engineer named Karl Jansky was working on a very practical problem. Radio antennae were picking up noise, static that interfered with communication, and he wanted to track down where it came from. In the process of solving that problem, Jansky discovered something nobody was looking for. Some of that noise was not coming from thunderstorms or from human equipment. It was coming from deep space. He had detected the first radio signals from beyond the Earth, and with that, the field of radio astronomy was born. As astronomers built better radio instruments and began to survey the sky, they found plenty of sources that made sense. There was Jupiter, crackling with radio emission. There was the Crab Nebula, the glowing wreckage of an exploded star. There were nearby galaxies, but scattered among those familiar objects were others that made no sense at all. They were small. They were faint. They were point-like, meaning they showed no shape or structure, just a dot. They emitted radio waves across a broad range of wavelengths, and crucially, when astronomers turned their optical and infrared telescopes to the same spots, they found nothing. There was no visible object there, just a pinprick of radio noise coming out of an apparently empty patch of sky. The only real clue these objects offered was their position, and their positions told a confusing story. They appeared both within the band of the Milky Way, the bright stripe of our own galaxy across the sky, and well outside it. Now, our galaxy is shaped like a thin disk. If you find objects scattered both inside that disk and far above and below it, there are really only two possibilities. Either the objects are extremely close to us, close enough that we are seeing them inside our local neighborhood, the way the visible stars of the night sky surround us in every direction, or they are extremely far away, so distant that they lie out in the wider universe beyond the flattened plane of our galaxy. Both options led somewhere uncomfortable. If these radio sources were close, then they should have been easy to see in ordinary visible light. Nearby objects are not invisible, and yet there was nothing there. But if they were extremely far away, then a different problem appeared, and it was a much worse one. To be detectable in radio waves at all from such an enormous distance, these objects would have to be pouring out a truly absurd amount of energy. If they were as distant as their positions suggested they might be, then they were, without competition, the brightest objects in the entire universe. It helps to understand just how recent and how fragile our knowledge of the universe was at that moment. The idea that other galaxies even existed, that the soft smudges astronomers called nebulae were in fact separate islands of stars far beyond our own, had only been firmly established a few decades earlier. Within living memory of the astronomers working in the 1950s, the entire universe had been thought to consist of nothing but the Milky Way. To go from that, from a cosmos that was a single galaxy to a cosmos of countless galaxies, had been a staggering expansion of the human picture of reality. And having just absorbed one enormous expansion, the field was, understandably, not eager to absorb another. The tidy, finite, slightly boring universe of clusters and voids felt like a hard-won resting place. The new windows onto the sky did not care about resting places. To appreciate why opening up the rest of the electromagnetic spectrum mattered so much, you have to remember how narrow our natural vision is. The light your eyes can detect is a thin slice of an enormous range. Beyond the red end lies infrared, then microwaves, then radio waves, each with longer and longer wavelengths. Beyond the violet end lies ultraviolet, then X-rays, then gamma rays, with shorter and shorter wavelengths. For the entire history of astronomy until the 20th century, we had been studying the universe through a keyhole, seeing only the one narrow band our biology happened to provide. Opening the other bands was like a person who had been deaf their whole life suddenly being able to hear. The universe had been speaking in all those other voices the entire time. We simply had no ears for them. Carl Jansky's discovery deserves a moment of its own, because it is a perfect example of how the most important findings often arrive sideways, unrequested. Jansky was not an astronomer hunting for cosmic signals. He worked for a telephone company, and his job was thoroughly practical. Transatlantic radio communication was being disrupted by static, and the company wanted to know where the static came from so they could deal with it. Jansky built a large, rotating antenna, and he carefully catalogued the sources of interference. Some of it was nearby thunderstorms, some was distant thunderstorms. But there was a third source, a faint, steady hiss, and it did something strange. It rose and fell on a cycle, and the cycle was not 24 hours long. It was a little shorter, and that small difference was the giveaway. A cycle slightly shorter than a day is the signature of the stars, not the Sunday. The hiss was rising and falling with the rotation of the sky itself. Jansky had found that the center of our galaxy was glowing in radio waves, and he had found it while trying to fix a telephone line. As radio surveys matured over the following decades, the catalogues filled up and the awkward objects accumulated. It is worth being precise about why they were so frustrating. An astronomer would record a radio source, note its position, and then turn the finest optical telescope available to that exact patch of sky, fully expecting to find a galaxy or a nebula or at least something. And there would be nothing. Or, sometimes, there would be a single faint dot that looked, for all the world, like an ordinary, unremarkable star. A radio source that looked like a star made no sense, because ordinary stars are not strong radio emitters. The thing was a contradiction sitting in the data, and a contradiction in the data is either a mistake or a discovery, and the only way to find out which is to measure more carefully. And so the stage was set for one of those moments that the history of science returns to again and again, a pile of anomalous data, a community of careful, intelligent people genuinely divided about what it meant. One camp insisting the objects must be relatively local because the alternative was an absurd brightness. The other camp following the positions and the numbers toward that absurd brightness, and refusing to flinch, neither side could win the argument with the tools of debate. The only thing that could settle it was a measurement precise enough to fix, beyond dispute, how far away one of these objects actually was. And as the 1960s opened, the techniques to make that measurement were, at last, almost ready. You can understand why astronomers pushed back hard against that conclusion. It is one thing to discover a new kind of star. It is another to claim you have found objects that outshine everything else in existence, when you cannot even see them with an ordinary telescope, and you have no idea what could possibly power them. The debate was not polite background chatter. It was a genuine argument about the size of the universe and about whether the laws of physics, as understood at the time, could even accommodate something so bright. And the strangest part is this. The astronomers arguing against the distant interpretation were not being foolish. They were being careful. They simply could not imagine a process violent enough to explain what the data was telling them. They were right to be cautious. They were also, as it turned out, completely wrong. The thing that broke the deadlock was not a new theory. It was a single, beautifully precise measurement, and it arrived in the early 1960s. Part 3. The night the distance was measured. The breakthrough came down to a problem of location. Radio telescopes in the early days were not good at pinpointing exactly where in the sky a signal originated. They could tell you roughly, but roughly was not good enough. To match a faint radio pinprick to a specific object, you needed to know its position with great precision, and the techniques to do that were only just maturing in the 1960s. One particular radio source had a catalogue name that gave nothing away. It was called 3C273, simply the 273rd entry in the third Cambridge catalogue of radio sources. And 3C273 happened to sit in a part of the sky that the moon passes across. This was an enormous stroke of luck, because it made possible a clever trick. When the moon drifts in front of a radio source, the radio signal cuts off at the exact instant the moon's edge crosses it, and switches back on the instant the moon's edge moves past. Since the position of the moon's edge is known with great accuracy at every moment, the timing of that cutoff and that return gives you an extremely sharp measurement of where the radio source actually is. Two astronomers, Cyril Hazard and John Bolton, used exactly this method, watching 3C273 wink out and back as the moon occulted it, and from that they pinned down its position with a precision nobody had achieved before. With that precise location in hand, the work passed to a Dutch-American astronomer named Martin Schmidt. Schmidt pointed an optical telescope at the exact spot Hazard and Bolton had identified, and there, in visible light, he found a faint object. It did not look like much. It looked like a slightly fuzzy star. But Schmidt did what astronomers do with any new object. He spread its light out into a spectrum, splitting it into its component wavelengths to read the chemical fingerprints written into it. Every element and molecule in the universe leaves a signature in light. Hot gas emits at specific, sharp wavelengths, producing bright lines. Cooler gas, in front of a light source, absorbs at specific wavelengths, producing dark gaps. Those bright lines and dark gaps form a pattern, and that pattern is a fingerprint. Astronomers had been reading these fingerprints for decades. Schmidt knew exactly what the common patterns looked like. The fingerprint of hydrogen, the most abundant element in the cosmos, was something he could recognize instantly. And the spectrum of 3C273 contained a pattern he recognized. The lines were there, the familiar fingerprint of ordinary elements, but they were in the wrong places. Every single line had been shifted altogether toward the red end of the spectrum, not by a tiny amount. The lines had been pushed redward by nearly 16% of their wavelength. The fingerprint was the universe's most ordinary fingerprint, and it had been moved bodily out of position. There were only two ways to shift a spectrum like that. Either the object was moving away from us at a tremendous speed, dragging the light to longer wavelengths the way a receding siren drops in pitch, or the object was extraordinarily far away, and the shift was cosmological. By this point, astronomers had been slowly coming to accept the Big Bang picture of the universe, the idea that the cosmos was smaller in the past and has been expanding ever since. Under that picture, light from a distant object is stretched simply because the space it travels through is expanding while it crosses, lengthening the waves into the red. The further away the object, the more space the light crosses, and the larger the redshift. When Schmidt worked through what a 16% redshift meant for 3C273, the answer was almost too large to accept. The object sat about 3.4 billion light-years away. It was the most distant object that had ever been observed, and not by a little. It beat the previous record by an order of magnitude. In 1966, Time magazine put Martin Schmidt on its cover and compared the scale of his discovery to the work of Galileo, writing that the 17th century Italian had startled scientists and theologians alike, and that the 20th century Dutchman had had an equally jarring effect on his own contemporaries. It is worth dwelling on the lunar occultation method itself, because there is a quiet beauty in it. The fundamental problem was that radio telescopes had poor positional accuracy. A radio dish could tell you that a source was somewhere within a fairly broad patch of sky, but somewhere within a broad patch is not good enough to point an optical telescope at. You need a pinprick, not a patch. The moon solved the problem by accident of geometry. The moon's own position and motion across the sky are known with exquisite precision, tracked and predicted to a fine accuracy. So when the moon's leading edge sweeps across a radio source, the radio signal does not fade gradually. It cuts off sharply, in an instant, and when the moon's trailing edge clears the source, the signal switches back on just as sharply. The exact times of those two events, the cutoff and the return, combined with the precisely known position of the moon's edge at each of those moments, triangulate the radio source's position to a sharpness that the radio telescope alone could never achieve. The astronomers had borrowed the moon as a ruler. Cyril Hazard and John Bolton timed the occultations of 3C273 and handed the astronomical community something it had never had before, a precise address for one of the mysterious radio sources. And it is a small, human detail worth noting that this was patient, unglamorous work. There was no single dramatic instant of revelation in the occultation timing. There was careful observation, careful calculation, and the steady narrowing of an uncertainty until a patch of sky became a point. Only then could the next stage begin. Now picture the scene as the work passes to Martin Schmidt. It is late in the year 1962, moving into 1963. Schmidt has the precise position. He points an optical telescope at it, and he finds the faint object waiting there, looking like nothing more than a slightly fuzzy star. He photographs its spectrum, spreading its light into a band of colours crossed by lines, and he brings that spectrum to his desk to read it, expecting, as anyone would, an ordinary result. Imagine being in the room with him. The spectrum is in front of him, a strip of light with its pattern of lines, and at first it does not make sense. The lines are not where the lines of any common object should be. For a while it looks like a jumble, an object made of something strange, lines that match no familiar fingerprint. This is the kind of moment that can go two ways. It can be dismissed as a bad measurement, an instrument error, a curiosity to be set aside. Or someone can look at it long enough and turn it over in their mind long enough to see the pattern hiding inside the apparent chaos. Schmidt looks, and then it arrives. The lines are not unfamiliar at all. They are the most familiar lines in all of astronomy, the fingerprint of ordinary hydrogen, the commonest element in the universe. They have simply been picked up all together as a set and moved. Shifted bodily toward the red by nearly 16%, the fingerprint was never strange, only its position was. And in the instant, Schmidt recognizes that. He knows what it means, because the arithmetic is not difficult once you see what you are looking at. A redshift, that large, red as cosmic expansion, places the object billions of light years away. He is sitting at a desk, holding a strip of light, and he has just understood that he is looking at the most distant object any human being has ever seen. There is a particular quality to that kind of discovery that is worth naming, because it is the emotional center of this whole first half of the story. Schmidt did not build a machine that forced the universe to be larger. He did not invent a theory that demanded it. He simply read what was written in the light, honestly, and followed the consequence without flinching from it. The universe was telling the truth about its own size all along, in every spectrum anyone had ever taken of these objects. It just took someone willing to believe the lines. When Time magazine put him on its cover in 1966 and reached all the way back to Galileo for a comparison, the comparison was not flattery. Galileo had pointed a new instrument at the sky and seen things that forced people to accept a universe they did not want. Schmidt had done the same. He had read a spectrum and handed his contemporaries a cosmos, an order of magnitude larger than the one they had been comfortable in. And, as we are about to see, 3C273 had arranged one final shock, and it had been hiding, patiently, inside the dusty archives of observatories for decades. Take a moment to feel what that measurement did. In a single stroke, it forced the universe to be vastly larger and vastly stranger than the tidy picture had allowed. Schmidt had not invented a theory. He had simply read the lines in a spectrum and followed the arithmetic where it led. And the arithmetic led to an object so distant and so bright that it rewrote the scale of everything. This is the first emotional weight of the Quasar story, and it is worth holding on to. A single human being, looking at a strip of light, discovered that the cosmos was far bigger than anyone had been willing to believe, and lived to watch the worldview of an entire field rearrange itself around what he found. But 3C273 had one more shock to deliver, and it had been hiding in plain sight for decades. Part 4. Smaller than the solar system. Once astronomers knew exactly where 3C273 was, they could do something they had not been able to do before. They could go back through the archives. Observatories keep their old photographic plates, the glass negatives on which generations of astronomers had recorded the sky. And when they dug back through those plates, they found that 3C273 had been photographed many times over many years. Earlier, astronomers had been capturing its image without ever realizing what they had. It had been sitting in their data, an unremarkable faint dot, for decades, but the archive held a clue. Comparing the old plates from year to year, astronomers noticed that the brightness of 3C273 was not constant. It varied. From one year's observation to the next, the object had measurably brightened and dimmed, and that single fact, the simple observation that it changed, turned out to be one of the most powerful pieces of evidence in the entire story, because of what it implies about size. Here is the reasoning, and it is worth going slowly, because it is one of those arguments that sounds almost too simple to carry so much weight. Imagine an object that brightens and dims as a whole. For the entire object to change its brightness together, some signal, some physical change, has to sweep across the whole thing. And nothing, no signal, no influence of any kind, can travel faster than light. So, if an object changes its brightness over the course of, say, 1 year, then the object cannot be larger than the distance light travels in 1 year. If it were larger than that, the far side would not yet have received the news of the change, and the brightness shift could not happen altogether. The timescale of the variation puts a hard ceiling on the size. 3C 273 varied within a year, which meant that 3C 273, an object more luminous than anything else known and more distant than anything else known, was also smaller than 1 light-year across. To put that in perspective, our entire solar system, out to the most distant comets, is a tiny thing compared to a light-year. This object was brighter than entire galaxies, galaxies that span 100,000 light-years and contain hundreds of billions of stars, and yet all of that ferocious output was coming from a volume that could comfortably fit inside the orbit of the planets. The light of 1,000 galaxies pouring out of a region smaller than the space around a single star. That is the moment the quasar problem became genuinely impossible. Astronomers now had not one absurd fact but two, and the two together ruled out every gentle explanation. Brighter than a galaxy, smaller than the solar system. Whatever this was, it was not a star, and it was not a galaxy, and it was not any combination of ordinary things. It was a new kind of object, and it needed a new kind of name. The technique of matching radio sources to faint visible light objects was now established, and astronomers used it to confirm the distances to dozens more of these so-called quasi-stellar radio sources. The clumsy name was a confession of ignorance. They knew these objects were not ordinary stars, but they had absolutely no idea what they actually were, so they simply described what they looked like, quasi-stellar, almost a star, but not. In 1964, the astrophysicist Hong-Yi Chu shortened the awkward phrase in the pages of the journal Physics Today, writing that for convenience, the abbreviated form quasar would be used throughout his paper. And so the quasar was born, named by an act of convenience, before anyone understood the first thing about what it was. As the discovery spread out of astronomical circles and into the public imagination, the word quasar took on a flavour of strangeness and remoteness. The physicist, George Gamow, even offered a new nursery rhyme for the occasion, a twist on the old one. Twinkle, twinkle, quasi-star, biggest puzzle from afar. How unlike the other ones, brighter than a billion suns. Twinkle, twinkle, quasi-star, how I wonder what you are. That last line was not just whimsy. It was an honest statement of the scientific situation. Astronomers had found the brightest objects in the universe, and they genuinely did not know what they were. The archival photographic plates deserve a moment of appreciation because they are one of the quiet treasures of astronomy. For more than a century, observatories had been recording the sky onto glass plates coated with light-sensitive emulsion, and crucially, they kept them. Plate archives are libraries of the past sky, drawer after drawer of glass, each plate a frozen moment of a particular patch of the heavens on a particular night. The astronomer who exposes a plate cannot know what future questions it will be asked to answer. The plates of 3C273 were taken by astronomers who had no idea they were photographing the most distant object then known. To them, it was an anonymous faint dot, not worth a second glance. And yet the dot was there, recorded faithfully, night after night, year after year, waiting for someone with the right question to come back and look. When astronomers did go back, knowing now exactly where to look, they found those years of images, and they noticed the variation in brightness. And the argument that the variation makes possible is so important and so often glossed over that it is worth walking through it once more, slowly and carefully, because it is one of the most elegant pieces of reasoning in all of astronomy. It rests on a single fact about the universe. Nothing, no object, no signal, no influence of any kind whatsoever can travel faster than light. That is not a limitation of our technology. It is a fundamental rule of how reality is built. Now think about what it means for an object to change its brightness. If a quasar grows brighter, then something has changed. Some physical event, somewhere in the object, has occurred. And for the whole object to look brighter to us, That change has to make itself felt across the entire object. Information about the change has to propagate from wherever it started out to every part of the thing, and that information cannot move faster than light. So picture an object that is, let us say, 10 light years across. Some change happens on one side of it. The far side will not even begin to know about that change for 10 years, because that is how long the light, or any signal, takes to cross. The object simply cannot brighten as a coherent whole on a timescale shorter than the time it takes light to cross it. The light crossing time sets a floor on how fast the whole object can vary. Turn that around and you have a ruler. If you observe an object varying its brightness over the course of a single year, then the object cannot be more than about 1 light year across, because if it were larger, it could not coordinate a change that fast. 3C273 varied within a year. Therefore, 3C273 was less than 1 light year across. And now hold the two facts together, because together they are the thing that broke astronomy. This object was more luminous than an entire galaxy, more luminous than 100 billion stars combined, and it was smaller than 1 light year, a region so small that our entire solar system would be lost inside it. The light of a galaxy, the light of more than a galaxy, was pouring out of a volume barely larger than the space around a single ordinary star. There is no gentle way to absorb that. It is not the kind of fact you can fold into your existing picture of the universe with a small adjustment. It demands a new kind of object, governed by a process of a ferocity that nothing in the familiar catalogue of stars and galaxies could supply. And the astronomers of the time felt that fully. The clumsy name they reached for, quasi-stellar radio source, was not a name at all. It was a written confession. It said, in effect, this thing looks a little like a star, and it is not a star, and we have no idea what it is. When Hong-Yi Chu compressed that confession into the single word quasar in 1964, he was naming an admission of ignorance. The word entered the language fast, and it carried a flavour of the alien and the remote. George Gamow's little rhyme, brighter than a billion suns, how I wonder what you are, was charming, but it was also an exact and honest summary of the state of human knowledge. We had found the brightest objects in all of creation, and the last line of the nursery rhyme was a real question that nobody could answer. To answer it, astronomers would have to stop staring outward at the impossible distant beacons and turn their attention to something much closer, much darker, and much quieter, hidden at the centre of our own galaxy. And the zoo only grew. As radio astronomy sharpened, astronomers found more variety than they knew what to do with. Some quasars were extraordinarily bright, and these brightest ones eventually earned their own name, the blazars. Others emitted no radio waves at all, but blazed instead in X-rays. There was Cygnus A, one of the brightest radio objects in the entire sky, which turned out to be a galaxy with a bright core and 2 thin jets reaching hundreds of thousands of light-years out into space, each ending in a gigantic bubble screaming with radio emission. Every one of these objects, loud or quiet, near or far, shared one feature. Their cores were abnormally, impossibly bright. In some of them, the nucleus alone outshone all the hundreds of billions of stars in the surrounding galaxy combined. Astronomers gathered them all under one umbrella term, active galactic nuclei, and then faced the obvious question. Something had to power them. And to find out what, they had to stop looking at the distant universe and look much closer to home. Part 5. The Monster Close to Home. 25,000 light-years from where you are sitting, in the direction of the constellation Sagittarius, there is a monster. You cannot see it. You could not see it with your eyes on the darkest night, and you could not see it directly even with the finest telescope ever built. And yet astronomers have known for decades that something strange was hiding there at the very centre of our own Milky Way galaxy. Before we follow the astronomers down into the galactic core, it is worth pausing on the strangeness of the situation they faced. They had, in the distant quasars, a problem of impossible brightness, and they had a suspicion, growing slowly, that to solve a problem about light, they would have to study a thing that gave off almost no light at all. There is a lovely irony in that, and it runs through this whole part of the story. The key to the brightest objects in the universe turned out to be the darkest. Consider what it actually takes to find a black hole at the center of the galaxy. You cannot see it. It emits no light. It is buried behind 25,000 light-years of gas and dust that scatters and absorbs most of the wavelengths you might use to peer in. The center of our galaxy is, to ordinary optical telescopes, simply curtained off, hidden behind a thick haze. If you could somehow strip that haze away and see the galactic core directly, it would be one of the brightest sights in the entire night sky, a glowing region of crowded stars. But you cannot. The dust hides it. This, by the way, is exactly why the first hints of the galactic core came in radio waves. Radio waves have wavelengths long enough to pass through the interstellar dust relatively unbothered, sailing through the haze that stops visible light cold. The astronomers saw the core in radio first, for the same reason you can hear a conversation through a wall that you cannot see through. The wall is transparent to one and opaque to the other. Now, think about the patience required to weigh the invisible thing. The astronomers found, deep inside the Sagittarius A region, individual stars, and they did not just photograph them once. They tracked them year after year after year, watching their slow progress across the sky, building up, observation by observation, the shapes of their orbits. This is genuinely a long-term commitment. A star near the galactic center can take years or even decades to complete a single orbit, and you cannot know the orbit until you have watched a meaningful arc of it. So for years, astronomers returned to the same patch of sky and measured the same stars, and slowly, gradually, the orbits emerged from the data. Tight loops swung around a single common point, and around that point there was nothing visible. The stars were clearly orbiting something. Their looping paths demanded a central mass, the way the planets demand the Sunday, but the center of their orbits held no star, no glowing object, nothing the telescopes could detect. The mass was there, and the light was not. When the astronomers applied the basic mechanics of orbital motion, the arithmetic that has worked flawlessly since it was first written down centuries ago, the central object came out at more than 4 million times the mass of the Sunday. 4 million suns, dark, compact, and silent. Now let me take you down into that core, because numbers on their own do not convey what kind of place it is. Imagine you could travel inward from where we sit, out here in the quiet suburbs of the galaxy, toward the center. For a long time, the journey would be much like our own neighborhood, stars scattered thinly across enormous gulfs of empty space. But as you approach the core, the character of the place would change. The stars would crowd together, packed into a volume far smaller than they occupy out here, an inner city of suns. You would pass through a vast, cold ring of dust, a torus roughly 1,000 light-years thick, a slow-turning wall of smog so tenuous that you would barely notice passing through it, and yet so effective at absorbing light that it curtains the whole core from outside view. And then, within that ring, you would feel the physics change. Out in the galaxy, the motion of things is governed by the combined gravity of billions of stars. But inside that ring, in the innermost region, one object dominates everything. Every star, every clump of gas, every speck of dust within that region moves to the command of a single dark mass. You would have crossed from the galaxy's territory into the black holes, and at the very center of it, you would find the thing the EHT photographed in 2022, a fuzzy ring of superheated plasma around a core of perfect blackness, a black hole whose gravity bends the light from behind it up and over its own horizon, unfolding the far side of itself into view, showing you a shadow that is larger than the object that casts it. And yet, for all its menace, our black hole is quiet. It is a sleeping giant, not a roaring one. The distant quasars outshine it millions of times over, which left astronomers with the question that drives the rest of this story. The thing in our core is a supermassive black hole, and it is calm. The distant quasars are blindingly violent. Could they possibly be the same kind of object in two different states? And to even ask that seriously, they first had to prove that black holes were real at all, that extreme gravity reaches out into the black hole's surroundings. Any star that wanders too close risks being torn apart, its material shredded and pulled into a doomed spiral. And yet, here is the strange and important fact. Despite all of that, the supermassive black hole at the center of our galaxy is, by cosmic standards, quiet. It is nothing like the distant quasars, whose luminosities run millions of times higher. From outside our galaxy, you would barely notice that a supermassive black hole was here at all. So astronomers had found a 4 million solar mass black hole sleeping in our galactic core. The distant quasars were impossibly bright. The obvious question almost asked itself, could the two things be connected? Could a black hole, of all things, be the engine that powers a quasar? To answer that, they first had to be sure that black holes were real at all. Part 6. Could it really be a black hole? It is easy, from where we stand now, to forget how radical the idea of a black hole once was. When astronomers first floated the notion that black holes could power quasars in 1964, just a year after the first quasar had been identified, most of their colleagues rejected it outright. And they were not being unreasonable. At that time, black holes were considered a wild, probably unphysical hypothesis, a mathematical curiosity, rather than a real feature of the cosmos. The reasoning behind the skepticism was sound. Einstein's theory of general relativity, published earlier in the century, had certainly been a radical reshaping of our understanding of gravity. But the fact that a theory is radical does not mean every strange solution buried in its mathematics has to be built somewhere in the real universe. The idea of a black hole was that matter could compress so tightly, collapse so completely, that no force in nature could withstand the inward pull, and the matter would fall all the way down to a point of infinite density. To many physicists, that sounded absurd. Surely, they reasoned, some process, some pressure, some resistance would step in and stop a dying star before it crushed itself out of existence entirely. What changed their minds was an object in the constellation Cygnus, the Swan. It is known today as Cygnus Zon, and it announced itself as a bright source of X-ray radiation. Astronomers spent years trying to understand how a star could be producing so many X-rays. Then, in 1972, observations by the astronomers Louise Webster, Paul Murdin, and Charles Thomas Bolton revealed the answer. Cygnus Zon was not one star. It was two, and one of the two was invisible. The X-rays were not coming from the invisible companion itself. They were coming from the swirling plasma surrounding it, gas that was being pulled off the visible star and was spiraling toward the invisible one. By studying the motion of that gas, astronomers could calculate the mass of the unseen companion and, more importantly, its density. And, whatever it was more compact than any known star and more compact than any star could possibly be. The numbers pointed, uncomfortably, to a black hole. The skepticism of the era is captured in a famous wager. The physicist Stephen Hawking, who would later become one of the great theorists of black holes, actually bet against Cygnus Zone, containing one. He wrote about it in his book A Brief History of Time, explaining that when the bet was made in 1975, he was about 80% certain that Cygnus Zone was a black hole, and that by the time he was writing, in 1988, he would put the figure at about 95%, though the bet had still not formally been settled. 10 years after the book, he finally conceded. Cygnus Zone was the first confirmed black hole, and Hawking, in losing his bet, helped close the case. Once black holes were known to be real, the whole picture began to click into place. The universe clearly knew how to make stellar mass black holes from the deaths of massive stars. And it was reasonable to think that those black holes, given enough time and enough material, could merge with one another and swallow gas, swelling steadily until they reached truly enormous masses. Such giants would naturally end up in the centers of galaxies, where matter piles up most densely, including, of course, the galaxies hosting active nuclei. Observations soon confirmed it. Everywhere astronomers looked, every galaxy seemed to host a supermassive black hole at its center. To understand why the cores of galaxies are exactly where you would expect these giants to form, you have to think about how structure grows in the universe. The Big Bang picture tells us that the cosmos changes with time. Long ago, matter was spread out almost perfectly smoothly, with only the faintest differences in density from one place to another. But gravity is patient, and gravity is relentless. On the largest scales, gravity is the only force that matters, and where matter is concerned, it is always attractive. A patch of slightly higher density pulls in its neighbors. That makes it denser still, which makes its pull stronger, which draws in even more matter. It is a feedback loop with no natural break, and over hundreds of millions of years, it drives the smallest variations into the first stars, the first clusters, and the first galaxies. It is genuinely difficult, from our vantage point, where black holes appear in films and children know the phrase, to feel how outlandish the idea once was. So, it is worth reconstructing the discomfort honestly. The mathematics that describes a black hole had been sitting inside Einstein's general relativity since not long after the theory was published. The equations permitted a solution in which matter collapsed completely, all the way down, until it formed a region of space from which not even light could escape. But the existence of a solution in a set of equations is not the same as a promise that nature builds it. Equations can contain mathematical possibilities that the universe never realizes. Many physicists, including for a long time Einstein himself, suspected that the black hole solution was exactly that, a mathematical artifact, something that would never actually form because some physical process would always intervene. And the intuition behind that suspicion was reasonable. We are surrounded, in everyday life, by examples of matter resisting compression. Squeeze a gas, and its pressure rises and pushes back. Solid matter resists being crushed. The whole of ordinary experience teaches that when you push on stuff, the stuff pushes back, and the harder you push, the harder it resists. So the idea that you could push matter so hard that nothing, no pressure, no resistance, no force in nature whatsoever could stop it from collapsing all the way to a point, sounded like a violation of everything intuition knew. Surely, the reasoning went, a dying star would find some way to steady itself. Surely something would catch it. This is why the case of Cygnus Zone mattered so much, and why it is worth telling carefully. Cygnus Zone announced itself, in the early days of X-ray astronomy, as one of the brightest X-ray sources in the sky, a fierce glow of high-energy radiation in the constellation of the Swan. X-rays are the signature of extremely hot, extremely energetic processes, and astronomers wanted to know what could be generating so much of it. For years, the answer was unclear. Then, in 1972, the astronomers Louise Webster, Paul Murdin, and Charles Thomas Bolton resolved the puzzle. Cygnus Zone was a binary. It was two objects orbiting each other. One of them was an ordinary, visible star. The other was invisible. And here is the crucial step in the reasoning. The X-rays were not coming from the invisible object directly. They were coming from a swirl of superheated plasma around it, gas torn from the visible companion star and spiraling inward toward the invisible one, heated to ferocious temperatures as it fell. By studying the motion of the visible star and the behavior of that hot gas, astronomers could calculate the mass of the unseen object, and they could estimate how compact it had to be. The result was uncomfortable. The invisible companion was more massive than the heaviest a dead star could be while remaining any known stable object, and it was more compact than any ordinary star could possibly be. By elimination, the candidates ran out. The thing was, in all likelihood, a black hole. The famous wager captures the mood of the era with a kind of human honesty that pure data never can. Stephen Hawking, who had already done foundational theoretical work on black holes, made a bet against Cygnus Son actually being one. He described it in his book, A Brief History of Time. When the bet was struck, in 1975, he put his confidence that Cygnus Zone was a black hole at around 80%. By 1988, when he was writing the book, he had raised that to about 95%, but he had not yet conceded the bet. Some years later, he finally did. Cygnus Son became widely regarded as the first confirmed black hole, and a leading theorist of black holes had lost a bet by being too cautious about their reality. There is something fitting in that. Even the people building the theory found the conclusion hard to fully trust. Once that trust was established, the larger picture assembled itself with real momentum, and it is worth seeing why each step felt natural. The universe makes stellar mass black holes routinely, as the endpoints of massive stars. Black holes can grow by swallowing gas and by merging with one another. Growth concentrates them where matter concentrates, which is in the dense cores of galaxies. And the cores of galaxies are exactly where the abnormally bright active nuclei live, the chain of reasoning pointed, link by link, toward a single conclusion. The engine inside a quasar was a supermassive black hole. Observations soon confirmed the universal part of the claim. Look at essentially any large galaxy, and at its center you will find a supermassive black hole. They are not rare. They are standard equipment. But standard equipment or not, an enormous conceptual problem remained, and it was the problem that this entire investigation had been circling from the start. A black hole is a thing that pulls. It is pure inward gravity. It takes, it does not give. So how, by any logic, could the most purely inward, most purely devouring object in the universe be the source of the most spectacular outpouring of energy in all of creation? That is the question the next part finally answers. All of that gravitational pile-up produces extraordinarily high densities in the cores of these structures. The center is simply where the matter ends up. The cores of galaxies are crowded with stars, and the stars that form there tend to be far more massive than average. Massive stars live fast and die young, and when they die they leave behind black holes. Packed into such a small volume, those black holes merge together again and again, growing without restraint, climbing toward the supermassive scale. So the logic was clean. Black holes exist, they grow. They settle in galactic cores. And the cores of active galaxies, the quasars, are abnormally bright. The connection seemed almost inevitable. There was just one enormous problem standing in the way. A black hole is, by definition, a region of pure gravity. It only pulls. How could something that only pulls on matter possibly produce the most ferocious outpouring of energy in the universe? Part 7. The engine is falling. Here is the answer, and it is so simple that it is almost disappointing right up until the moment you realize how strange it is. The energy of a quasar does not come from any exotic process. It comes from falling. The most powerful engine in the universe runs on the same thing that pulls a dropped cup toward the floor. To see how falling can release so much energy, we need an idea called binding energy, and the cleanest way into it is a simple picture. Imagine a pile of stones sitting at the bottom of a deep valley. You decide you want to move that pile up to the top of the surrounding ridge. To do it, you have to pick up each stone and carry it up, and every time you do, you are spending energy to overcome the pull of gravity, lifting the stone against the slope. If you wanted to know how much energy the whole job would take, you could add up the gravitational pull on every stone across the whole climb. Now, scale that picture up. Instead of a pile of stones, imagine the entire planet Earth. And instead of carrying the stones up a ridge, imagine pulling every single atom of the Earth so far out into space that it never comes back, dismantling the planet completely, atom by atom, against the pull of its own gravity. The total amount of energy that job would require is what physicists call the binding energy of the Earth. It is the energy that holds the thing together, and it is also, in reverse, the energy that would be released if all that matter fell back down again. Now apply the same idea to a black hole. Imagine taking a single particle and dragging it from just outside the event horizon all the way out to a distant orbit, thousands of light years away, fighting against the black hole's gravity the entire way. The energy that task demands is the binding energy of that particle. And, exactly as with the Earth, that energy works in both directions. The energy you would have to spend to haul the particle out is the same energy that gets released when the particle falls back in. For a typical supermassive black hole, that binding energy is roughly equal to the entire rest mass energy of the matter itself. The matter falling in, just by falling, can liberate something close to the full energy locked up in its own mass. The process is not perfect. Not every scrap of available energy gets released as the particle falls. In practice, only about 10% of the binding energy is converted into radiation and other usable forms. 10% might not sound like much, but you have to compare it to the alternative. The thermonuclear reactions in the heart of a star, the fusion that powers the sun and lights up every star you have ever seen, convert only about 0.1% of the rest mass energy of their fuel into energy. Falling onto a black hole is roughly 100 times more efficient at turning mass into energy than the nuclear fire that powers the stars. The most violent engine in the universe is also, by a wide margin, the most efficient. Let that settle for a moment, because this is one of the genuinely unsettling realizations in physics. Gravity is the weakest of the four fundamental forces. It is so weak that a small magnet can pick up a paperclip and overpower the gravitational pull of the entire Earth. Gravity is the force you experience as nothing more dramatic than things falling, as the ordinary, gentle, constant downward tug you have felt every second of your life. And that force, the weakest one, the gentle one, is what runs the most powerful engine in the cosmos. Every time you drop something and watch it fall, you are watching, in miniature, the exact same process that lights up 1,000 galaxies at the core of a quasar. The difference is only one of scale. There is something almost poetic about the answer, and it is worth letting the strangeness of it land properly before we work through the physics. We have spent this entire journey building toward the most violent object in existence, and the source of its violence turns out to be the gentlest, most familiar phenomenon in your daily life. Things fall. That is the whole secret. The quasar runs on falling. The reason that works, the reason falling can be a power source on this scale, is an idea called gravitational potential energy, and the binding energy picture is the cleanest way to feel it. Return to the pile of stones at the bottom of the valley. When a stone sits at the bottom, it is, in a precise physical sense, in a low place. To lift it to the ridge, you must spend energy, and that energy does not vanish. It is stored. The stone at the top of the ridge holds, in its raised position, exactly the energy you spent lifting it, and the moment you let it go, that stored energy is handed back, converted into the motion of the falling stone, and then into heat and sound as it lands. A high stone is a loaded spring. A low stone is a spent one. The depth of the valley sets how much energy is in play. Now here is the part that makes a black hole special. The depth of the valley around a black hole is not like the depth of any valley on Earth. It is the deepest gravitational well that the universe permits to exist. The amount of energy stored in the difference between far away and close to the event horizon is colossal, because the well is so profoundly deep. When you let matter fall down that well, the energy released is correspondingly colossal. For a typical supermassive black hole, the binding energy in play is roughly equal to the entire rest mass energy of the matter itself, the full energy locked inside its mass by the most famous relation in physics, the equivalence of mass and energy. Falling down a black hole's well can liberate something close to the total energy content of the thing that falls. In practice, the engine does not extract all of it. Roughly 10% of the binding energy is converted into radiation and other useful forms as matter spirals in. The rest is carried across the event horizon and lost, or otherwise not radiated. 10% can sound modest, even disappointing, until you set it beside the only other large-scale energy source the universe runs on, which is nuclear fusion. Fusion is what powers stars. It is the process at the heart of the Sun, the welding of light atomic nuclei into heavier ones, and it is genuinely powerful. But fusion converts only about 0.1% of the rest mass energy of its fuel into energy. Compare the two numbers directly. Accretion onto a black hole at 10% against fusion at 0.1%. Falling onto a black hole is on the order of 100 times more efficient at turning mass into energy than the nuclear fire that lights every star in the sky. The most violent engine in the universe is also the most efficient one, and it achieves that efficiency not through some exotic new physics, but through the brute simplicity of dropping things down the deepest hole that exists. This is the second great emotional weight of the story, and I want to give it room because it genuinely changes how you might see the world around you. Gravity is the weakest of the four fundamental forces by an enormous margin. It is so feeble that the entire mass of the Earth, every atom of the whole planet pulling together, can be defeated by a small magnet lifting a paperclip, or simply by your own arm raising a cup off a table. Gravity is the force you experience as nothing more than the quiet, constant, unremarkable fact that things have weight, that dropped objects fall, that you are gently held to the ground. It is the most ordinary force there is, and it is the force that runs the most powerful object in the universe. Every time you have ever watched something fall, a leaf, a coin, a drop of rain, you have watched, in perfect miniature, the exact physical process that lets a quasar outshine 1,000 galaxies. The only difference between the leaf falling to your floor and the matter falling into a quasar is the depth of the well. The principle is identical. The most extraordinary thing in existence runs on the most ordinary thing you know. But there is one more piece to set in place before we move on, and it is the piece that separates an engine from an explosion. We have established where the energy comes from. We have not yet established why it comes out slowly. If every scrap of matter destined for a black hole simply fell in all at once, you would get one stupendous flash, and then darkness, a single event, brief and finished. A quasar is not brief. It burns steadily for millions of years. Something is metering the fall. Something is taking what could be an instantaneous detonation and rationing it out into a long, patient, controlled burn. The energy source is falling, but the engine, the thing that turns that falling into a sustained and regulated output, is more subtle, and to see it, we have to follow the gas itself on its long descent. But there is a subtlety, and it is the subtlety that makes a quasar an engine rather than a bomb. If all the matter destined to fall into a black hole simply crashed in at once, you would get a single titanic flash, and then nothing. That is not what a quasar does. A quasar shines steadily for millions of years. The release of energy is not a sudden detonation. It is slow, and it is staged. It is a steady, controlled build-up, with material continuing to crowd inward, releasing its energy in installments. Something is regulating the flow, metering the fall, keeping the engine burning at a steady, ferocious rate instead of blowing itself out in an instant. And understanding what does that regulating means watching the gas on its long, doomed journey toward the event horizon and discovering that the engine, remarkably, controls its own throttle. Part 8. The piston. To see how a quasar regulates itself, follow a clump of gas as it falls. As gas spirals inward toward the supermassive black hole, it heats up. Compression and friction force its temperature higher and higher, and hot gas radiates. Up to this point, there is nothing surprising. Hot things glow. That is ordinary physics. But around a quasar, the intensity of the radiation crosses a threshold where something genuinely strange begins to happen, and it changes everything. The discovery that a quasar regulates itself is, to my mind, one of the most beautiful turns in the whole story, because it reveals the engine to be something far more sophisticated than a simple gravitational drain. It has a feedback loop. It has, in effect, a governor, a self-correcting mechanism, and the engine built that governor out of nothing but its own light. To see how, we follow the gas. As gas spirals inward toward the supermassive black hole, it heats. We have touched on this, but it is worth being precise about why. Two things heat the gas. The first is compression. As the gas is funneled into a smaller and smaller volume, it is squeezed, and squeezing a gas raises its temperature, the same reason a bicycle pump grows warm in your hand as you compress the air inside it. The second is friction. The gas is not moving in a single calm stream. Different streams of gas, at different distances from the black hole, move at different speeds and rub against one another, and that rubbing, that internal friction, converts orderly motion into heat. Compressed and chafed, the infalling gas climbs to enormous temperatures and hot matter radiates. So far, this is unremarkable physics. Hot things glow. What is remarkable is what the glow does. We are used to thinking of radiation, of light, as something insubstantial, something that warms but does not push. And in everyday life, that is essentially true. The light from a lamp falls on your hand, and you feel only gentle warmth, no force. But light does carry momentum, and therefore light can, in principle, push. The push is simply far too feeble to notice under ordinary conditions. Around a quasar, conditions are not ordinary. The radiation streaming out of the white-hot infalling gas is so overwhelmingly intense that its pressure becomes a genuine, commanding physical force. The light does not merely warm the surrounding gas, it shoves it. Picture a sunlight so fierce that it could physically knock a person to the ground, not by heat, but by sheer pressure, and you have the right mental image for the environment near a quasar. And now the feedback loop closes, and it closes in a way that is almost elegant enough to feel designed. The radiation from the heated gas pushes outward on the gas that is still falling in. It drives that gas away from the black hole, but gas that has been driven away can no longer fall in, and gas that cannot fall in can no longer feed the engine. So the engine, by shining, starves itself. With its fuel supply pushed back, the radiation weakens. And as the radiation weakens, the outward pressure weakens with it until there is no longer enough push to hold the gas back. Gravity, which never stopped pulling for an instant, reasserts itself. The gas cools, condenses, and begins once more to fall inward, and as it falls it heats, and as it heats it radiates, and the radiation builds until it is once again strong enough to push the gas away. Collapse Ignition, starvation, cooling, collapse again. The cycle turns and turns. The car engine comparison is exact, and it is worth taking seriously rather than treating as a loose metaphor. A piston engine does not let its fuel explode all at once. If it did, you would not have an engine, you would have a bomb, a single destructive blast. Instead, the piston meters the combustion into a rhythm, stroke after stroke, and that rhythm is what converts a violent chemical reaction into smooth, sustained, usable power. The radiation pressure cycle of a quasar does precisely the same job. It takes what could be a single catastrophic infall and rations it into a steady rhythm of feeding and starving. And that rationing is the reason a quasar can shine not for a brief flash, but for millions of years without interruption. The engine's restraint is the source of its endurance. Now I want you to feel the piston from the inside, because to understand a quasar you should not only watch it, you should, for a moment, be the gas. So become a single parcel of gas, drifting in the crowded, turbulent region a few light days out from the black hole. You are being pulled inward. You feel no rope, no hand, only the patient, irresistible pull of the deepest well in the universe, and you begin to fall. As you fall, you accelerate, and as you accelerate you are pressed harder against the gas crowding around you, and the pressing makes you hot. You were dark, and now you begin to glow, dimly at first, then with a fierce light pouring out of you in every direction. And then you feel it, the strangest sensation of the descent. The light, your own light, and the blazing light of everything falling alongside you, presses back against you. It is a real force, an outward push, and it lifts you, slows your fall, stalls you, and then drives you gently back outward, away from the dark. You rise, you cool, your glow dims and then fades, and as it fades, the push that was holding you up fades with it, and gravity, which has been waiting the entire time, takes hold of you once more. You begin, again, to fall. You are not plunging cleanly into the black hole. You are riding the piston, stroke after stroke after stroke, one small parcel of matter in the slow, patient, self-regulating rhythm that keeps the brightest thing in the universe alight. And yet even this, even the elegant throttle of the piston, is not the whole engine. Because the gas around a black hole does not merely fall in and out, it also spins. And spinning gas, it turns out, builds something far more dangerous than a piston. Now I want you to imagine being inside that process, because it is one thing to describe the piston from the outside and another to feel it. Picture yourself as a single parcel of gas, drifting in the crowded region a few light days from the black hole. You are being pulled inward, and as you fall you pick up speed, and as you pick up speed you are compressed against the gas around you, and you grow hot. You begin to glow, faintly at first, then fiercely, your own light pouring out of you. And then you feel it, the radiation, your radiation, and the radiation of everything falling around you, pressing back against you, an outward force lifting you, slowing your fall, pushing you back up and away from the dark. You drift outward, you cool, the glow fades, and as the glow fades, the push fades with it, and gravity, which never stopped pulling, takes hold of you again. You begin, once more, to fall. You are not falling into the black hole in one clean plunge. You are riding the piston, stroke after stroke, part of the slow, patient rhythm that keeps the brightest thing in the universe alight. And yet, even this, the piston, the throttle, the steady rhythm, is only the beginning of the engine. Because the gas around a black hole does not simply fall, it spins, and spinning gas builds something far more dangerous. Part 9. The disk and the dynamo. Gas does not fall straight into a black hole. It almost never does, and the reason is a principle you have felt with your own body, even if you have never named it. It is called conservation of angular momentum, and the everyday picture of it is a spinning ice skater. When a skater is turning with their arms stretched wide and then pulls their arms in close to their body, they speed up, they spin faster, and they did not push against anything to do it. The rotation was already there. Pulling inward simply concentrated it. The principle that turns falling gas into a structured engine is one you have felt in your own body, and it is worth grounding it there before we apply it to a black hole. It is called the conservation of angular momentum. The everyday demonstration of it is a figure skater. Watch a skater begin a spin with their arms stretched wide. They are turning at a certain rate. Then they pull their arms in tight against their body, and without pushing against anything at all, without any new effort, they suddenly spin much faster. The rotation they already had simply became concentrated. Spread out, it was slow. Pulled in close, it was fast. Rotation, once a system has it, is not easily given up. Pull the system inward, and the spin must increase to compensate. Gas falling toward a black hole obeys exactly this rule. Any gas drifting in from the wider galaxy carries some small initial rotation, some sideways drift, because nothing in a galaxy is ever perfectly still or moving on a perfectly straight line toward the center. As that gas falls inward, as it is pulled closer and closer to the black hole, its modest initial rotation concentrates, exactly as the skater's does, and the gas whirls faster and faster. This is why gas cannot simply drop straight down a black hole like a stone down a well. Its own growing spin carries it sideways even as gravity pulls it down. The inward fall and the sideways whirl combine, and the gas is forced into orbit, circling the black hole the way a planet circles a star, suspended in the balance between falling in and rushing past. The consequence is that the messy, loose cloud of infalling gas and dust does not stay a cloud. It organizes itself. It settles and flattens and tightens into a thin, dense, rapidly rotating disk wrapped around the black hole, like the grooves of a record wrapped around its hole. This is the accretion disk, and it is the part of the engine that actually shines, the part our telescopes see. Within that disk, the relentless compression and the friction between neighboring streams of gas moving at different speeds heat the material to staggering temperatures. The gravitational potential energy of all that infalling matter is being converted ceaselessly into heat and light. At its root, the disk is nothing more complicated than far too much matter trying to force its way into far too small a space and growing white-hot in the struggle. The disk glows most fiercely in ultraviolet light, but it radiates across a broad span of the electromagnetic spectrum, and it does more than glow. It flings out streams of cosmic rays, electrons and protons accelerated to within a whisker of the speed of light. These particles behave like microscopic, high-velocity bullets, and now and then one of them collides with a low-energy photon, a humble particle of infrared or visible light drifting nearby. In that collision, the fast particle transfers a share of its energy to the photon, and the photon is kicked violently up the spectrum, transformed into a high-energy X-ray. This is the origin of the X-ray glow that some active galaxies show. Those X-rays are, quite literally, the fingerprint of matter moving so fast that its collisions reshape light itself. But the disk's most consequential trick is magnetic, and to see it you have to remember what extreme heat does to matter. At the temperatures inside an accretion disk, atoms cannot survive intact. The heat tears the electrons away from the atomic nuclei, and what remains is a plasma, an electrically charged gas of free particles, the same fundamental state of matter you see in a stroke of lightning or the surface of the Sunday. And here is the fact that everything now turns on. Moving electric charges generate magnetic fields. This is not exotic. It is the basic principle behind every electric motor and every generator on Earth. A disk of swirling, charged plasma is automatically and unavoidably a machine for generating magnetism. At the start, the field is weak, and its lines of force simply ride along with the gas, looping in lazy circles around the black hole. But the disk does not turn as one rigid plate. The inner regions, deep in the black hole's grip, orbit far faster than the outer regions. This difference in speed, this differential rotation, drags the magnetic field lines along at different rates in different places, winding them, coiling them, twisting them ever tighter, and a coiled, twisted magnetic field stores energy the way a wound spring does. The turbulence of the disk makes it worse still. The flow is not smooth, it is chaotic, full of eddies and clumps and churning currents, and every clump that drifts and tugs on a field line stretches and distorts it further, while the differential rotation keeps twisting the loops around themselves. This whole churning, self-amplifying process has a name, and it is the same name as the device that generates electricity in a power station. It is a dynamo. The dynamo takes the chaotic, turbulent tumbling of the disk and converts it steadily and relentlessly into an ever stronger magnetic field. Ordinarily, a magnetic field has little say over the bulk motion of matter, but as the dynamo drives the field strength higher and higher, a threshold is finally crossed, and the magnetic forces grow strong enough to seize command, to dictate where the gas goes rather than merely drifting along with it. The engine has now grown itself a set of magnetic muscles, wound tight and loaded with energy. And those muscles are about to reach down toward the spinning black hole at the center and turn its rotation into the most far-reaching weapon in the universe. This whole churning, twisting, self-reinforcing process has a name. It is a dynamo. A dynamo takes chaotic, turbulent motion and converts it steadily into an ever stronger magnetic field. The dynamo around a supermassive black hole takes the messy tumbling of the accretion disk and feeds it into a magnetic field that grows and grows. Ordinarily, magnetic fields have only a tiny influence on the bulk motion of matter, but as the dynamo ratchets the field strength higher and higher, a threshold is crossed. The magnetic forces become strong enough to seize control, to dictate where the gas goes rather than merely following it. The engine has now built itself a set of magnetic muscles, and those muscles are about to do something spectacular. They are about to reach down toward the spinning black hole itself and turn its rotation into a weapon. Part 10. The Jets. We have built most of the engine now. We have the black hole, the source of gravity, we have the accretion disk, the glowing structure of infalling matter. We have the radiation pressure piston, the throttle that meters the fall, and we have the dynamo, the magnetic field that the disk's own turbulence has wound into something powerful. But we still have not explained the most dramatic feature of all, the thing the very first astronomers actually detected, the radio pinpricks, the long, thin jets of Cygnus A reaching hundreds of thousands of light years into the dark. Where do the jets come from? Before we trace where the jets come from, it is worth standing back to take in how much of the engine we have already assembled, because the picture has become genuinely intricate and each piece earns its place. We have the black hole itself, the bottomless gravitational well that supplies the energy. We have the accretion disk, the flattened, white-hot structure of infalling matter that does the shining. We have the radiation pressure piston, the self-regulating throttle that meters the fall and lets the engine burn steadily for millions of years instead of detonating once. And we have the magnetic dynamo, which has taken the disk's own turbulence and wound it into a powerful, energy-loaded magnetic field. That is a remarkably complete machine, and yet it still does not account for the single most dramatic feature of all, the feature the very first radio astronomers actually stumbled upon without knowing it. The jets. The thin, straight beams of Cygnus A reaching hundreds of thousands of light years out into the dark, ending in their screaming radio bubbles. Where do the jets come from? The honest scientific answer is that the jets are not completely solved, and a good science channel should say so plainly rather than smoothing it over. But there is a leading explanation, and it is one of the most elegant ideas in modern astrophysics. It is called the Blandford-Znaeck process, after the two physicists who worked it out. And it depends on a property of the black hole that we have, until now, left unused. The black hole is not just sitting there, it is spinning. A spinning black hole does something that has no counterpart anywhere in ordinary experience. It drags space-time itself around with it. To get a feel for this, picture setting a heavy table down on a thick, soft rug and then slowly rotating the table. The rug does not stay still beneath it. Gripped by friction, the rug is twisted around along with the table, winding up underneath it. A rotating black hole does this to the very fabric of space and time. It winds space-time around itself. And close to the black hole, there is a region where this winding becomes utterly irresistible, where space-time is being hauled around so forcefully that nothing whatsoever can hold still against the current, no matter how powerfully it tries. That region is called the ergosphere. Anything that enters the ergosphere is compelled to rotate along with the black hole. It is not a matter of choice or of force that can be resisted. It is simply how space and time behave there. And, crucially, for our story, that compulsion applies to magnetic field lines just as much as to matter. So, bring back the powerful magnetic field that the dynamo has spent so long building. The strong field lines threading the inner accretion disk reach in and out of the ergosphere, and the moment they enter it, the dragging of space-time forces them to whirl around with the black hole, twisting them, coiling them, winding them up on themselves. Twisted tight and forced to find an outlet, the field lines punch outward along the one direction left open to them, away from the black hole's poles, above and below the plane of the disk, building two great coiled columns of magnetic energy that tower out from the black hole's spin axis. Charged particles caught on those field lines are channeled along them, funneled by the magnetic structure. Most of the particles riding field lines that pass near the black hole are simply swept across the event horizon and lost from the universe forever. But some of them ride lines that only barely graze the danger zone, and these particles are not swallowed, they are flung. Accelerated by the colossal magnetic energy concentrated in the ergosphere, they are hurled outward, and guided by the twisted columns of field, they stream away from the black hole in two long, thin, tightly focused jets. They are lighthouse beams, fired straight out of the galactic core into the surrounding dark, at speeds approaching the speed of light itself. As those particles race along the length of a jet, the magnetic field forces them into tight spirals, and a charged particle forced to spiral radiates. The light it pours out is mostly in radio waves, and there, at last, is the resolution of the mystery we began with. The loud radio sources, the faint, baffling pinpricks scattered across the sky that started this entire investigation decades ago, were the radio glow of magnetized jets streaming out of supermassive black holes in the cores of distant galaxies. Recall how this story opened, with quasars described as lighthouses in the deep beacons of unknown power. That description is no longer a poetic mystery. It is now a precise, mechanical fact. A quasar is, in the most literal possible sense, the universe's most powerful radio transmission tower, broadcasting across billions of light years on the energy of matter falling down a hole. And the reach of the jets is almost impossible to overstate. The particles within them move at nearly the speed of light and carry such immense energy that they do not stop at the edge of their home galaxy. They punch straight through it, through the entire spiral of stars, and keep going, driving out into intergalactic space for distances of up to millions of light years. Eventually they lose momentum, slowed as they plough into the thin gas that fills the space between galaxies, and where they finally come to rest they pile up into vast, glowing, high-pressure bubbles of charged particles. And those bubbles carry heat. They carry it from the innermost region of the engine, a region only light days across, outward into the volume of an entire cluster of galaxies, a structure that can span more than 1,000,000 light-years. Hold that scale in your mind. A single object, an engine smaller across than our solar system, reaching out to raise the average temperature of an entire cluster of galaxies, the largest gravitationally bound structures the universe contains. So let me set you down outside a galaxy, at an enormous distance, and let you watch this happen, because the scale of it deserves to be felt and not merely stated. You are looking at a quasar's host galaxy as a whole, a spiral of hundreds of billions of stars hanging in the dark. From its brilliant core, a thread of light erupts. It is so straight, so narrow, so perfectly focused that it looks almost manufactured, almost artificial, and it does not stop at the edge of the spiral. It crosses the rim of the galaxy and keeps going, a needle of pure radiance crossing a gulf of emptiness so vast that the light you are watching leave the far tip of that jet departed it long before there was a single ocean on the earth. And at the end of that immense thread, the jet finally blossoms, opening into a bubble of glowing charged gas wide enough to swallow 1,000 galaxies, wide enough to warm an entire cluster. One object did all of that. One engine, a region of space smaller than the orbit of the planets, reaching out across more than 1,000,000 light-years to touch and heat and reshape the largest structures in existence. That is the true measure of the most powerful thing in the universe. And now that we have seen the whole of the engine, every part of it, from the gravitational well to the disk to the piston to the dynamo to the jets, we are finally able to ask the questions that the engine, for all its elegance, cannot answer. Stand back from a galaxy and watch this happen. Picture yourself at an enormous distance, looking at a quasar host galaxy as a whole. From its bright core, a thread of light erupts, a jet so straight and so focused that it looks almost artificial, and it does not stop at the edge of the spiral of stars. It keeps going and going, a needle of radiance crossing a gulf of emptiness so wide that the light you are watching leave the jet's far end, departed it long before there were oceans on the earth. And at the end of that thread, the jet blossoms into a bubble of glowing, charged gas, wide enough to hold 1,000 galaxies, wide enough to warm a whole cluster. One object did that. One engine, smaller across than our solar system, reaching out to touch and heat a structure 1,000,000 light-years wide. That is the scale of the most powerful thing in the universe. And now we have seen the whole engine, every part of it, which means we can finally ask the questions that physics still cannot answer. Part 11. Too bright, too big, too early. We have, by now, assembled a complete picture of the quasar engine, and it is a triumph. The supermassive black hole, the ring of dust around it, the ferocious accretion disk, the metering piston of radiation pressure, the dynamo, the magnetized jets. This single picture explains an astonishing range of observations. It even explains why we see so many apparently different kinds of active galaxy. If we view a galactic core face-on, we see the intense radiation of the accretion disk combined with the radio glow of the jet, and we call it a quasar. If we happen to be looking straight down the barrel of one of the jets, we get the most extreme emission of all, and we call it a blazar. And if a thick, cold ring of dust, a torus 1,000 light-years across, happens to lie between us and the core, it blocks our view of the engine entirely, and we see something quieter. It is, as one description beautifully puts it, like humanity first encountering cats one piece at a time. A whisker here, a paw there, a swishing tail. At first, they seem like completely different creatures. Only slowly do we realize they are all the same animal, seen from different angles. It is worth pausing to appreciate how much this single picture explains, because a good theory should be celebrated for its successes before it is interrogated for its failures. and the quasar engine is, by any measure, a triumphant theory. Consider how it dissolves what once looked like a bewildering zoo of separate objects. For decades, astronomers catalogued what seemed to be many different kinds of active galaxy, loud ones and quiet ones, radio bright ones and X-ray bright ones, blazars and quasars, and a host of other types. The engine picture reveals that most of this apparent variety is an illusion of perspective. It is the same object, a black hole with its disk and its dusty torus and its jets, seen from different angles. View the core face-on, and you see the disk's fierce radiation together with the radio glow of the jet, and you call it a quasar. View it straight down the barrel of a jet, and you receive the most extreme, most concentrated emission of all, and you call it a blazar. Let the thick, cold ring of dust, the torus 1,000 light years across, fall between you and the core, and it curtains the engine away, and you see something far quieter, and call it by yet another name. The beautiful comparison offered earlier in this story holds perfectly. It is like the first human beings encountering cats, one fragment at a time. A whisker glimpsed here, a paw there, a swishing tail somewhere else. At first they seem like wholly different creatures. Only slowly does the realization dawn that they are all the same animal, seen from different sides. The engine picture also explains, cleanly, the curious absence of quasars in our cosmic neighborhood. A quasar is not a permanent fixture. It is a phase, and a phase requires fuel. To shine, the engine must be fed a steady supply of fresh gas. Cut off that supply, and the entire machine shuts down, every part of it. No infalling gas, so no accretion disk. No disk, so no dynamo. No dynamo, so no twisted magnetic fields, and therefore no jets. The whole engine goes dark. Now consider how the universe has changed over its history. The early universe was small and crowded, its galaxies packed close together, colliding and merging constantly, and every merger funneled a fresh flood of gas into a galactic core and lit a new round of quasar activity. But the universe today is old and vast and thinly spread. Galaxies are far apart. Mergers are rare events. The fuel supply for most galaxies has dwindled. And so the quasars of the nearby, present-day universe have, almost all of them, gone dark. They have run out of fuel. Our own galactic core is one of these darkened engines. Quiet now, though, as we are about to see, its quiet is not permanent. So the engine works, and it explains a great deal, and we genuinely understand it. And yet, for all of that, there are three things about quasars that stubbornly refuse to fit the picture. And it is important to be honest that these are not tidy, solved footnotes. They are open wounds in our understanding, live and unhealed. Stated plainly, the quasars we observe are too bright. The supermassive black holes that power them are too big, and they appear in the history of the universe too early. Too bright, too big, too early. Three short phrases, and each one names a genuine crack running through an otherwise triumphant theory. Take too big and too early together, because the two are knotted into a single problem. We know, with confidence, only one reliable way to manufacture a black hole, and that is the death of a massive star, which means the first black holes in the universe could not have come into being until the first generation of stars had been born, lived out their lives, and died. And if those first stars resembled the stars we see around us today, the black holes they left behind were small, no more than a few times the mass of the Sunday. So the puzzle is this. From seeds of just a few solar masses, how do you build a black hole of more than 1 billion solar masses? And how do you do it fast? A growing black hole has only two methods available. It can merge with other black holes, and it can accrete matter. And, frustratingly, each of those two methods runs straight into a wall. The wall that merging hits has a name that has become almost famous among astronomers. It is the final parsec problem. When two black holes first drift into each other's neighborhood, their interactions with the surrounding stars and gas allow them to spiral gradually inward toward one another. But eventually, that surrounding material is exhausted, and the only mechanism left to draw the two black holes closer is the gravitational waves they radiate as they orbit, ripples in the fabric of space-time that carry energy away and let the orbit slowly tighten. The trouble is that gravitational waves are exceedingly weak. Once the two black holes have closed to within a few light years of each other, that last stretch of separation, the final parsec, the emission of gravitational waves alone would take longer than the entire present age of the universe to bridge. The black holes should, by that arithmetic, be stuck, and yet we know with certainty that black holes do merge. We have caught the gravitational wave ripples of merger events directly with our detectors. We find a single black hole sitting in the cores of galaxies that have demonstrably suffered many separate mergers over their history. The universe has plainly found a way to solve the final parsec problem. We simply do not know what that way is. And accretion, the second route to growth, has its own wall, and we have already met its bricks. The very same seesaw of radiation pressure and gravitational collapse that we praised as the engine's elegant self-regulating throttle, the piston that lets a quasar burn steadily for millions of years, also imposes a strict limit on how fast gas can be delivered to the black hole. Push too much material inward too quickly, and the radiation that material produces blows the rest of the supply back out before it can ever fall in. This speed limit on accretion is called the Eddington limit. It is not an absolute, unbreakable law of nature, and there may be ways around it, but it is a serious and stubborn obstacle, and it makes the rapid growth of an early black hole genuinely difficult to explain. Compounding all of this is a strange and telling absence in the data. If black holes grow gradually from small seeds to supermassive giants, we ought to see intermediate mass black holes scattered everywhere, the in-between class, heavier than a stellar black hole but lighter than a supermassive one, the visible evidence of growth caught in the act. But we barely find them at all. And then there is the single most pointed piece of evidence, the most distant quasar known, catalogued as J0313-1806. That object was already a fully assembled engine, its central black hole well over 1 billion times the mass of the Sun, when the universe was a mere 670 million years old. That is only about 5% of the universe's present age. Too bright, too big, too early, the engine runs, beautifully and comprehensibly. We simply cannot fully explain how the universe ever found the time to build it. And accretion, the other route to growth, has its own wall. The very same seesaw of radiation pressure and gravitational collapse that keeps a quasar shining steadily also limits how fast gas can reach the black hole. Push too much material inward too quickly, and the radiation it produces blows the rest back out before it can fall in. This is called the Eddington limit. It is not an absolute, unbreakable law, but it is a serious obstacle, and it makes the rapid growth of an early black hole genuinely hard to explain. Compounding everything is a strange absence. We should see intermediate mass black holes everywhere, the in-between class, heavier than stellar black holes, but lighter than the supermassive giants, marking the stages of growth. But we barely find them, and the most distant known quasar, an object catalogued as J0313-1806, was already a fully assembled engine with a black hole well over 1 billion times the mass of the Sun, when the universe was only about 670 million years old. That is just 5% of its present age. Too bright, too big, too early. The engine runs. We just cannot fully explain how it was ever built. Part 12. The Giant Will Wake. Faced with 3 mysteries that the ordinary story cannot solve, physicists have begun to reach for stranger explanations, and it is worth meeting them, because they are serious science, even where they are speculative. One possibility is that dark matter, the invisible substance that makes up roughly 80% of the mass of every galaxy, can collapse directly into black holes. In the simplest models, dark matter does not interact with itself and cannot easily clump on small scales. But in richer models, where dark matter can occasionally interact with itself, it could clump rapidly in the dense early universe, and if enough of it gathered into a small enough volume quickly enough, its own gravity could trigger a catastrophic collapse into a giant black hole, one large enough to begin powering a quasar before the first stars had even formed. Faced with three mysteries that the ordinary star and merger story cannot resolve, physicists have begun reaching for stranger explanations, and these deserve a fair and careful hearing because even where they are speculative, they are serious science, grounded in real physics rather than invented from nothing. The first possibility concerns dark matter, the invisible substance that makes up roughly 80% of the mass of every galaxy. In the simplest models, dark matter does not interact with itself at all, and therefore cannot easily gather into dense clumps on small scales. But there are richer models in which dark matter can, occasionally and weakly, interact with itself. In such a model, dark matter could clump rapidly in the dense conditions of the early universe, and if enough of it gathered into a small enough volume quickly enough, its own gravitational weight could trigger a catastrophic runaway collapse straight into a giant black hole, a seed already large enough to begin powering a quasar before the first star had ever shone. A second possibility holds that our assumptions about how stars form simply do not apply in the early universe. In the cosmos today, a collapsing cloud of gas can only grow so large before heavier elements within it allow it to radiate away its heat efficiently, cool, and fragment into ordinary stars. But the early universe was almost entirely free of those heavier elements, because forging and scattering them takes many generations of massive stars living and dying. Without that efficient cooling, the first clouds may not have fragmented in the ordinary way. The first stars may have grown to hundreds of times the mass of the Sun, true giants, and when such giants died, they would have left behind correspondingly giant black hole seeds, far heavier than anything stellar death produces today. And there is a third idea, stranger than either, which proposes that black holes have been present since the very first moments of the Big Bang itself. In this picture, the exotic conditions and violent phase transitions of the universe's first few seconds spawned countless small black holes directly. Primordial black holes, born before the first star, before the first galaxy, before there was any structure at all. Most populations of primordial black holes have been ruled out by careful observation, but a surviving remnant could provide a shortcut to quasar building, bypassing the slow route of stars entirely. And it is precisely to test ideas like these, to probe directly the first stars, the first galaxies, and the first quasars, that the James Webb Space Telescope was built and launched. The mystery of the earliest quasars is not a closed case. It is one of the live frontiers of physics, being actively investigated right now. But here is the thread I most want to pull as we draw toward the close, because it is the thread that transforms the quasar from a remote cosmic curiosity into something far more personal, far closer to home. In the early years of the 2000s, astronomers made a genuinely startling realization. It is not simply that every large galaxy hosts a supermassive black hole at its center. It is that the properties of the black hole and the properties of the entire surrounding galaxy are intimately and tightly linked. The more massive the black hole, the more massive the galaxy it sits within. The two quantities track each other across an enormous range. Black holes and the galaxies that contain them do not grow up independently as separate and unrelated things. They grow up together, their fates entwined. And the quasar phase turns out to be part of the very mechanism by which they grow up together. When a galaxy takes in a great flood of new material, whether by gravitationally drawing in surrounding gas or by cannibalizing a smaller neighboring galaxy, a large share of that material spirals down into the core, forms an accretion disk, ignites a jet, and turns the core into a quasar. The radiation pouring out of that quasar then floods the entire host galaxy and heats its reservoirs of gas. And gas that has been heated too much cannot collapse efficiently to form new stars, so the quasar acts as a brake. It prevents the galaxy from burning through all of its gas in one sudden, wasteful, runaway burst of star formation, and instead it spreads that star formation out into a steady, measured, sustainable trickle that can continue for billions of years. Consider how strange and how important that is. The most violent object in the universe is also, in this role, a regulator, a governor, a mechanism that prevents a galaxy from squandering its own future in a single spendthrift episode. And this applies directly to us, to our galaxy, to the chain of events that allowed you to exist. The Milky Way grew the way all large galaxies grow, by merging with and devouring smaller galaxies over billions of years, and any one of those mergers could have flooded our galaxy with so much gas that star formation ran wild and exhausted the entire supply in just a few 100 million years. But Sagittarius A star, our own central supermassive black hole, held us in check. It is genuinely possible, not as idle speculation but as a serious scientific consideration, that without Sagittarius A star flaring as a quasar somewhere in our galaxy's distant past, the Milky Way would have spent its gas far too quickly, and our Sun, which formed relatively late in the galaxy's long history, might never have had the chance to form at all. The most terrifying object in the universe may be standing somewhere near the root of the reason you are here at all, alive, and able to be terrified by it. But this quiet equilibrium that we currently enjoy will not last. Cast your mind back to the monster we met at the heart of our galaxy, 25,000 light-years away, 4 million times the mass of the Sun, dormant. Remember that dormant does not mean dead. It means sleeping, and we have already seen the physical evidence of the last time the sleeper stirred. In the year 2010, astronomers using the Fermi Gamma Ray Space Telescope discovered two enormous regions of hot plasma reaching far above and far below the plane of our galaxy, each of them more than 50,000 light-years across. These are the Fermi bubbles, and they are fossils. They are the slowly cooling scars left behind by a feeding event a few million years ago, when something, perhaps a cluster of stars, perhaps a wandering clump of interstellar gas, fell into the maw of Sagittarius A star, and the very same physics we have spent this entire long journey carefully assembling, the disk, the dynamo, the jets, went briefly and ferociously to work in our own galactic core. And it will happen again, on a scale beyond anything the Fermi bubbles represent. In roughly 5 billion years, our Milky Way will begin to merge with the great spiral of the Andromeda Galaxy, our nearest large neighbour, already falling toward us through the dark. The two galaxies will pass through each other and fall together, and in time, their two central supermassive black holes will find each other and eventually merge into one. The violence of that collision will tear stars and nebulae to shreds, and the tattered remnants of all that destroyed material will come pouring down toward the new combined core. And when that material arrives, the slumbering giant at the center will wake. It will draw the wreckage into a disk, light its engine of gravity and magnetism once more, and pour its fierce, tireless radiation out into the new galaxy, ending any hope of a quiet sky for ages to come. We began this journey with monsters lurking in the dark, things that seemed safely far away, comfortably remote in the deep cosmic past, observed from a great and reassuring distance. But the most powerful thing in the universe was never only out there. The same engine, the very same kind of monster, sits at the center of the galaxy you live in tonight. It is patient, it is quiet, and one day, by nothing more dramatic or more exotic than the simple act of something falling, it will wake. And it will happen again on a far greater scale. In roughly 5 billion years, our galaxy will begin to merge with our nearest large neighbour, the Andromeda Galaxy. The two galaxies will fall together, and their two central supermassive black holes will find each other and eventually merge. The collision will tear stars and nebulae to shreds, and the tattered remains of all that destroyed material will pour down toward the new combined core. And when it does, the slumbering giant at the centre will awaken. It will light its engine of gravity and magnetism once more, and it will pour its fierce, tireless radiation into the new galaxy, ending any hope of a quiet sky for ages to come. We began with monsters lurking in the dark, far away and safely distant. But the most powerful thing in the universe was never only out there in the deep cosmic past. It is here. It is at the centre of the galaxy you live in. It is patient and it is quiet, and one day, by the simple act of something falling, it will wake.